Yes, my name is Nicola Orsini. I'm a researcher and I'm an associate professor of medical statistics at Karolinska Institutet in Stockholm, Sweden. And I have been using Stata since 2001, so about 20 years. I started with Stata 7, now it's Stata 18, and my plan is, first of all, thanks to the organizers of this webinar, and I'm going to introduce you to very basic commands in Stata. They're very useful to get things published. And so what I'm going to do, the strategy that I'm going to follow is very, very simple. I'm going to fire up a Stata session, and I will have a PDF of a top medical journal, and I will show you how you can reproduce, the main findings in this paper. So it's a very, very practical approach. There is no theory. If you have Stata up and running, you can try to follow what I'm doing, what I'm typing. And so it's going to be a very, quick tour of fundamentals of Stata language. So the first thing that I'm going to do is to start off Stata 18. And I have a Mac, and Stata is cross-platform. So if you have Windows or Mac, you don't see any difference. You launch the program, and you will see something like this. We have the Stata result window, you have the command window. And those are the two most important windows. The command window is where you can type something in. You're saying, please, Stata, do something. And the Stata result window, you can see what you type and the results of whatever you type. And because this webinar is intended for people doing research, and so the key thing of research is being reproducible. So I'm not going to use and type a lot of lines interactively, because all of this, it will be gone within 45 minutes. I'm going to write a do file, so we have some memories of this webinar, and I can share it with you at the end. And it's also the professional way of using any software, not just Stata. So I'm going to open a do file editor. It's the syntax file or batch file or script where I'm going to write everything we need. So I'm going to open a do file. It's called webinar. And in this text file here, we can write comments and commands and save it. So just to have a little bit of a plan for the next 45 minutes, what is going to happen? I'm going to show you how to read or import data, and we're going to produce some descriptive statistics, fit some multivariable models, and get some graphs of predictions from the model. And of course, I have to make some basic assumptions. There's no way we can interact at the moment, so I'm going to assume that you are interested in using Stata for research activities. I'm going to have to assume that you have some basic principle of statistics, so test of hypothesis, confidence interval, and you're familiar with popular regression models like linear and logistic. And I'm not going to focus on statistics at all, but it's inevitable that if you use a statistical software, you have to come across some statistics for sure. And so this is the do file that I'm going to share with you at the end of the webinar. And I'm going to write some live notes, and so which is also instructive for you if you want to follow up what I'm doing here. And I will try to go slow, especially in the beginning. Eventually, I have also some lines of code for more complicated things. So let's start with the challenge. What is the problem? The problem is that our task is, in 45 minutes, is to reproduce the main findings of this study. This is a prospective cohort study investigating the risk of hyponatremia among marathon runners. And so this is a study published in New England Journal of Medicine. The impact factor is probably 140 in 2005. And the idea of the study was to find out the risk factors for hyponatremia in marathon runners. So this was a study conducted in Boston in 2002. It's a prospective study. Everyone is free of the disease of interest. Everyone is great at the beginning of the marathon. And at the end of the marathon, they measure sodium concentration in blood. If sodium concentration goes very low, you're more likely to have health issues, eventually to die. So the whole idea is to identify risk factors for this hyponatremia. And the motivation is very simple. There's a 28-year-old woman who died after the Boston Marathon. And the ironic is that this woman did a PhD on the health benefits of running. And so after this sudden death, that was the motivation for doing this study. So enough with the background. So let's say we want to analyze this data set. Okay, so I'm gonna type in here the command to open the data set. So I'm gonna say reuse. I'm gonna make this a little bit bigger so you can see. Use to open a data set to read data in Stata format. So the Stata format is .dda. Use HTTP and here it is. So that's what we can type. Clear all. You specify the path of this file is statsforlife.se/data/marathon. So you can highlight those couple of lines, you can run it, and you have the data set everywhere you are. And use to open the data set, describe, so you can get the overall shape of the data set. As you can see here, there's a little note about attached to this data set. This is a label attached to data, just to have a reference. This is how many rows we have, 488. How many columns? 18 variables. So this is a typical data set used in medical research, and that's my area. So you have one line for each person and as many columns as many information you have on each individual. So describe is a very nice command to get the overall shape of the data set. You can see the variable names are typically short, ID, serum sodium concentration. This is the continuous outcome measurement at the end of the marathon, and this is the dichotomized outcome. This is what we're going to use, actually what the author use as to write down all the main findings. Then we have some female age and urine, some information about urine output, the body weight before and after, so the weight change, the height, BMI, the running time in minutes, training pace, how many numbers of previous marathons they did, the self-reported fluid intake, how much water they were drinking, if they were using anti-inflammatory drugs, and some categorization of weight change into intervals. And the data set is sorted by the ID. Okay, so ID is like a loop number, is a unique identifier of each individual. And so the data set is sorted by the ID from the lowest to the highest. So describe is an important thing to describe. I'm gonna write it here, describe. Get, how do you get the shape? How do you quickly get the shape and content of the data? Okay. And the other thing that is important to know when using Stata is, okay, how do you read? How do you import data set? How do you import data that are in different formats? Okay. So use is the command to open data set already in a Stata format. It's ready for the analysis. But let's say you have Excel file. The data are coming as Excel file or text tab delimited file. So instead we have this command import delimited. So let's say you have a text file. So a text file looks like this. Text. This is a text file. So you have all the columns of data, and of course it's very clean, and you can export as text file from any software. So let's say you want to import such a thing. Well, as long as you know the path, you know that this is a text file, and you have the var names on the first row. You see here we have typically in a text file you have the variable names on the first row. Okay, so on the first row you have the variable names. So we want to use the first line. We want to tell Stata, look, we have the variable names on the first line. So, and now I run this, and as soon as you try to import a new data set into the memory, you can see that Stata complains. They say, well, I'm sorry, are you sure? Because you already have some other data in the memory. So it's just warning us that you would lose, the previous data set. And that's fine, as long as is that what you want, you can simply say, before you're importing new data set, you can say clear the current memory, import the new data set, and describe. Describe. So if you run this, you can see all the variable names is the same size, 488 rows, 18 columns, and those are the variable names. There is no labels attached anymore because it's a very clean, text file. So if you want to attach some explanations like value labels or variable label, that is something that you have to do right after importing such a file. Let's say, so this is about importing text file. If you have an Excel file, import an Excel file into Stata, then the command is very similar. Rather than importing a tab delimited file, you're going to import an Excel. So, and the extension is XLS, and it's usually we have on the first row we have the variable names. So one more time, you say clear import Excel. The path where is located the file is up on the web, and please use the first row as the variable names for this new data set. Okay, and here you can see the variable name, and the variable label is the same as the variable name. Of course, this is something that you may want to change if you want to do some, if you want to make the data set a little bit more informative. Okay, so we have seen how to open a data set in a Stata format, in a text format, or Excel format. Okay, now we have the data set. We know the shape, 488 rows and 18 columns. And of course, we have an outcome of interest, and which is, the definition of the outcome is very important. And based on the outcome, everything follows. So let's start with the abstract of the paper. So as you can see here, results. Let's look at the results. Of 766 runners enrolled. So at the beginning of the marathon, they invited 766 runners, and there is no response. Only 488 runners, so only 64%, provided a usable blood sample at the finish line. Some people were enrolled, but then they didn't show up for the measurement of the outcome. So in this data set, we only have the respondents, 488. No respondents are gone. We still have some missing data for the risk factors, for the covariates or predictors of the outcome. But if you don't have the outcome, those have been kind of dropped out of the data. So we only have, in this data set, we have count. Let's do some counting, basic count. In this data set, we have 488 marathon runners. Count is a very basic command, very easy to use. You simply say count, and you count how many rows are in the data. You can count if serum sodium concentration is less than or equal 135 millimole per liter. And how many cases do we have? 62. And I'm going to say total number of total respondents. Okay. And of those total respondents, the other thing is how many number of cases, number of runners with serum sodium concentration Na less than or equal 135 millimole per liter. Okay, so count if you specify an expression. Expression is like filtering the data. You just want to count how many rows are satisfying this expression. So you can see 62 cases. And so the first number to present on the second line is 13% had hyponatremia. Okay, a serum sodium concentration 135 millimole per liter or less. Okay, so we have the counts, the absolute counts. So the incidence of hyponatremia, the incidence, how many cases, how many runners develop hyponatremia over the marathon, incidence of hyponatremia is 62 divided by 488, and this is about 0.13. How can you use Stata to do this simple calculation? You can use display if you have to compute something. Display 62 over 488. Okay, multiply by 100, you will get the instance of hyponatremia, which is about 12.7% that you can round to 0 decimal values as 13%. That's the first. So the second sentence in the results is simply showing the overall occurrence of this binary outcome. How many runners develop hyponatremia? The second part here is 0.6% have critical hyponatremia, so 120 millimole per liter or less. Okay? Hyponatremia is continuous, and so you can set different cutoff for defining what is a low values of serum sodium concentration. So you may think of different cutoff. So here they present also the instance of critical hyponatremia, when the serum sodium concentration is 120 millimole per liter or less. So if I want the instance of critical hyponatremia, what is the instance of critical hyponatremia? And this is defined as Na less than or equal 120 millimole per liter. So what I'm going to do is simply to count. You simply count. If Na is less than or equal to 120, you see how many they are. Okay, it's 3 persons. So this way, 3 out of 488 multiplied by 100, this is 0.6%. Okay, 0.6%. If you want, whenever this way is the command to customize the output. So you can also, right before the expression, you can specify the display format. So let's say you want to round. You're writing a paper, you can see here, you round this percentage to 1 decimal value, 0.6. So there's a fixed format for this, it's 2 digits and round the number to 1 digit after the decimal separator. So you can type this, 0.6. Display the format and the expression. Okay, so this is very useful when you're writing papers. You just want to use Stata as much as possible to get close to the numbers that you want to present. So you can copy and paste and write a sentence about it. So this is overall occurrence. What is the fraction of runners with a very low value of sodium concentration? Then the rest of the analysis, they are done with this definition of the outcome. Serum sodium concentration less than or equal 135, and for that, we have a variable. Now let me write here. We have a variable. So what is the binary outcome? Distribution. This empirical distribution of the binary outcome. Okay. So what is a one-way table? One-way table of counts. How do you do this? Well, one-way table of counts is simply is like running a couple of times this. How many people, how many cases you have, how many known cases, or simply tabulate. Tabulate is the command for one-way or two-way tables. So you can see here the univariate frequency distribution of the outcome. So you can count how many cases, 62, how many known cases, 426. You get the relative frequency, like 12.7%. You get also the cumulative empirical probabilities. So tabulate is a table of counts and relative counts. And we're going to use, again, tabulate for two-way tables. It's a classical, epidemiological table or medical table where you have a treatment, intervention, an exposure in general, and in relation to an outcome. So tabulate descriptive statistics of a categorical variable, and let's see how to describe table 1. Let's describe, now that we have a couple of sentences describing the overall occurrence of the disease, let's fill in here table 1. Table 1 is descriptive statistics. So we are describing this sample descriptive statistics stratified by sex. We have the male runners, the female runners, and whether they are reporting at the finish line, so respondents and no respondents. So Now, in this data set, we only have, that I got from the principal investigator, I only have the respondents. So what we can do right now is to present descriptive statistics of the data, age, body weight, BMI, running time, and so on, among men and women. Okay? So we only have stacks to stratify summary statistics. And so, as you can see here, we have for continuous variables, we have the mean, sample mean, and sample standard deviation, rounded to 1 digits. For binary data, we have the percentage, non-white race, it's 9, 10%. This is continuous variable body weight, sample mean and sample standard deviation. Same thing for BMI, same thing for training pace. For number of previous marathons, you see number of previous marathons is very skewed, so they show the median, the 25th, and the 75th percentile observed in the data. For example, here, how many self-reported use of anti-inflammatory drugs, also this is a percentage. 51% of the men use anti-inflammatory drugs as compared to 60%. So as you can see, table 1, if you want to fill this table, you need to be able to control what kind of summary statistics you want to present, and eventually how you want to stratify, and how you want to present the numbers. Eventually some rounding, some control of the display format. So let's see how we can fill in table 1. Descriptive statistics of data of the sample by sex, by females. Okay, so we do have a variable, tabulate female. Okay, we have a variable 0, 1. Are you a woman? Yes or no. So we can see that there's about 34% are women and 66% are men. Okay, so we need to present descriptive statistics by female sex. So tabulate is for a table of counts, but actually we don't need the counts. We need to know what is the distribution of some baseline characteristics. So what you can do is to use the summarize command, summarize age if female equal to 0. Okay. I want to summarize statistics of age in among men and women. So if you look at the syntax, there's an action, a variable, and a condition, an expression. So if you run these two, you're going to get the numbers that you need. You can see, okay, we get 320 men, the average age is 40 plus or minus 9.5, and 166 women, average age a little bit younger, 36 plus or minus 8.6. And so if you want to get this in one shot, you have tabstat command, age by female, and if you want to control the statistics, you can say mean standard deviation. Okay, and if you want to control the display format, you say 2.1f. Okay. Also, this is quite nice because in a single line, you can specify stratification, what kind of summary statistics, and the format. And so you see 40.3 plus or minus 9.5. You can copy this into a table. And I want to finish up with, for example, for a number of previous marathons, median, 25th, and 75th. How do you get this? The same command. So we have number of previous marathon by female. What kind of statistics? I want to see the median, P25 and P75. Display format, it doesn't matter because it's already an integer number. So you can see median, 25th and 75th, those are the three numbers shown in the table, number of previous marathons among men and women. The final thing, it would be, for example, this self-reported use of anti-inflammatory drugs. We have a binary predictor, a binary variable 0, 1, indicating whether someone reported using anti-inflammatory drugs. So a percentage is just an average of a 0, 1 variable. So that's easy to do. So you're going to say tabstat and set. So this is a variable anti-inflammatory drugs by female. Okay, I want to see the mean. And the format, this is going to be the average of a 0-1 variable is going to be a probability. So I want to see this with 2 decimal values. And eventually you can multiply by 100 to put it as a percentage in a table. So you can see that 51% of the men use anti-inflammatory drugs versus 60% of the women using anti-inflammatory drugs. So you can put these two numbers here and there. So this is table 1. Summarize if or tab stat by, controlling what kind of summary statistics. Let's see another thing here in the results section. Let's look at this paragraph here. At the finish line, the runners had a mean sodium concentration 140 plus or minus 5, ranging from 114 to 158. Okay, so what is the command to get this? Well, the results summarize NA. Among in the sample of 488 monitor runners, the average serum sodium concentration is 140 plus or minus 5, ranging from 114 to 158 millimole per liter. If you want to customize this, well, you can also use tab stat NA, stat mean, standard deviation, mean and maximum value. You can also control the display format, percent, let's say 2.1F, just 1 decimal values. The number that matters is the second number. Okay, you can see here 140. Actually, I don't want to see 0 decimal, just round to an integer number. So you can say 2.0. So 140 plus or minus 5, ranging from here to there. So that's the first. This is a sentence of descriptive statistics in the result. This is the result section. And the other sentence here is instead a 2 by 2 table, cross-classifying the runners according to hyponatremia status, yes or no, and female sex, yes or no. So you can see here 13%, 62 of 488 had hyponatremia. We have seen this with count, and then it's stratifying this by sex. So 22% of women, so 37 of 166, and 8% of men, 25 of 322 men. Okay, so how do we get this? This is a two-way table, so I'm going to use the, so this is also tabulate, NAS 135, I cross-classifies runners by binary outcome and binary indicator for sex. And so you can see here the 2 by 2 table. So 37 cases out of 166 among the women, 25 out of 322 among the men. So you can show the absolute counts. Typically, we also add column percentages. So you can say, well, 37 out of 166 is 22% versus 8% of men. Okay, so absolute counts, relative counts in the results section. Another thing, free runners had critical hyponatremia, and also you get a list of them. So those free extremely low values below 120 millimole per liter are 119, 118, 114. Again, those are really data points, extremely low values of serum sodium concentration. So how do you do this? Well, you can, well, the instance of critical hyponatremia, we have already done it over here. You just count if NA is less than or equal 120. And if you want to look at the smallest values of serum sodium concentration, I'm going to show you this. You can use, there is an option of summarize, which is detail. So you get more descriptive statistics of a continuous variable. So summarize in a comma, which is indicating separating the option from the main command. So you can see that the output is very different. You can see all the percentiles, the median, all the percentiles from 1 to 99, the free smallest values. So if you sort the variable, outcome variable from the lowest to the highest, those would be the free smallest values of serum sodium concentration, 114, 118, and 119. And you can write this, in the results section. So enough with descriptive statistics. Now we're going to move to the table 2. Table 2, you start, this is a sequence of univariable analysis. For every possible risk factors of hyponatremia, they show the mean standard deviation of this risk factor in the two levels of the outcome, cases and non-cases, and they conduct a t-test or Pearson chi-square test or Fisher exact test or non-parametric test for comparing the distribution of each risk factor in relation to in the two outcome levels, cases and non-cases. Okay, so this is a series of univariable statistics, and then you have also multivariable analysis. So they just put together BMI, running time, and weight change. So those are the three main risk factors for hyponatremia, and they use a logistic regression model to derive those odds ratios and test the hypothesis. Okay, so let's see how we can reproduce this table with Stata. And typically in a good paper, you can see that they also mention how you can do it. All continuous variables were analyzed with the use of a t-test. All categorical data were analyzed with the Fisher exact test. And for the number of previous marathons, which is very skewed and integer numbers, they use a non-parametric Wilcoxon-Ransom test. Okay, so let's do this. Let's fill in this table here very quickly. So table 1 done. Table 2. So if you want to t-test, I want to compare the average distribution of age among in the two outcome levels. Is going to be t-test age by. So here you can see the summary statistics or statistical inference for the age in the two outcome levels, and then you get here a two-sided p-value. This is what is shown in the output over here. This is a two-sided p-value here, 0.52. And typically, there is a variety of way of doing the t-test, and in this paper they're using. And they're assuming unequal variability of the continuous risk factors in the two levels. It's called t-test assuming unequal variability of the predictor in the two outcome levels. So this is the 0.52, and you can put it here. So this is descriptive statistics, mean and standard deviation of age in the two levels of the outcome, plus a formal statistical test on the difference in average age. So couple of lines. Substat age, stat mean and standard deviation, format 2.1f by stratified by the outcome status, NAS 135. Okay, descriptive statistics plus a test of hypothesis of equality of two means. And the other thing is instead another thing for categorical data, for example, for female sex. For female sex, you see is 60, this is column percentage, it's a fraction of women among cases and non-cases. So it's huge difference, 60 and 30%. So how do we get this? Well, categorical data were analyzed with a Fisher exact test. So you just cross-classify the subject by, actually this is, you cross-classify randomness by outcome and sex. I'm gonna add also the row percentages. So I can see here that row percentage is just a fraction of women among cases and non-cases, 60 versus 30%, and an overall p-value testing independence between, gender, sex, and hyponatremia status. And for continuous data, categorical data, for discrete data like number of previous marathon, they use a non-parametric test like rank sum previous marathon by NAS 135. So it's a formal test. The p-value is very small, and so this is a non-parametric test comparing the distribution of number of previous marathons in the two outcome groups. Okay, so you can see 0.008, and the median here, the median is 3 and 5, and we know how to get that with Substat. Now, so this is a sequence of univariable analysis. Continuous risk factor like body mass index, they did two types of analysis. One is comparing the average of the risk factor in the two outcome levels, or categorizing. This is very common in medical research, categorizing a continuous predictor in 3 levels, less than 20, 20 to 25, above 25, and then use categorical data analysis for it. So as you can see, all the odds ratios are coming upon categorization of BMI, categorization of running time, and categorization of weight change. and then they fit a univariable logistic regression model. I want to show you another thing. We have a few minutes left, so I'm sorry to rush over it. I want to talk about a couple of figures. Figure one is showing the gradient in the risk of hyponatremia across categories of weight change. You see why weight change, the change in body weight before and after race, is a strong predictor of hyponatremia. You know, the more the gain during the marathon, 3 to 5 kilos, they have a 70% higher risk of hyponatremia, and the risk is going down when they're losing weight. So this is a scatter plot. You know, the most important graph in this data is a two-way, two-dimensional graph. So this is a scatter plot showing where the height of the bar is the risk of hyponatremia, the height of the black bar is the risk of severe hyponatremia, defined as being less than 130 millimole per liter. You get some sample size on top of the bar and some p-value from a simple, Fisher exact test or Pearson chi-square test. So the way you do this in Stata is simple. So you set aside, I'm using extension of generate. I just want to store the average of a 0-1 variable within each level of weight change categorized. And then we also create an indicator. We express this by 100. We do the same thing for, we create an indicator variable for having severe hyponatremia. Severe means sodium concentration less than 130. Then we get also the total sample size, and we do a very large scatter plot, two-way. So once we have the $7 to present on the y-axis, and then we're going to simply graph them. So that's essentially it. So you can see this. This is the scatter plot relating risk of hyponatremia to weight change categorized. As you can see here, I see 1 to 7. Whether in the paper you can see the labels attached, and I see 1 to 7 because I have to open the data set in Stata format. We have with some labels attached. So you can see here the graph. If you want, once you're happy with that, you can just copy this into a Word document and you're done. And then you write a legend, figure 1. And the other thing is figure 2. Figure 2 is coming, which is another important figure, which is because it's summarizing. So we have different panels. So those are adjusted odds ratio for weight change, panel A, running time, panel B, and body mass index as predictors of hyponatremia. Okay, so we have panel A, B, and C. So you can see adjusted odds ratio estimated from a single multivariable model, where you can see some predicted adjusted odds ratios coming from a linear function. So it's a parametric approach to model a continuous predictor, a linear function for running time, and a quadratic function for body mass index. So those are nice figures because you're putting together prediction from a multivariable logistic regression model. You're drawing some statistical inference for a selected values, selected comparison, and it's enough to estimate a single model to get this figure. So I'm going to show you how. So open the data set. Okay, I'm going to use a quadratic function for BMI. So you have to generate BMI to the power of 2. Running time is in minutes, so I express this in hours divided by 60. And I fit a single multivariable model, logistic regression model. So we have those 3 continuous risk factors, and we plug in weight change and running time as they are. So it means using a linear function and a quadratic function for BMI. So let's do this. And then Stata has this beautiful past estimation command. So you can extract, it's called partial prediction, predict NL. So you're storing the adjusted log odds ratio simply as beta 1 multiplied by the distance between weight change and the chosen reference. The reference is 0 for weight change, 3 hours and a half for running time, and 22.5 for BMI. So here I'm extracting so you fit the model, extract those adjusted odds ratios, and at the same time, I also get the lower and the upper bound. So I get the dashed line in one shot, exponentiate a quick loop to exponentiate all these point estimates are based on the logic of the outcome probability. And then I can do the graph. And in the graph, I'm gonna add the position of, you see here is the position of the cases and the position of the known cases throughout the range of the continuous predictor. So this is a graph combining adjusted predictions and some observed data. So that's what I'm gonna do. So I'm gonna identify and just gonna put a spike. This is called a spike at the location of the individuals. So I'm gonna run this, and I'm gonna run all of that, and I'm gonna combine all the figures into one. Okay, so figure panel A, panel B, and panel C. And of course, so you have this. So you do the graph separately. So this is the adjusted odds ratio for weight change, the adjusted odds ratio for running time, and the adjusted odds ratio for body mass index. And then you combine all of them, and then you copy and paste into Word document, where you have your figure chart, and you write the legend. And of course, in terms of test of hypothesis, once you fit a logistic, multivariable logistic regression model like this, there is past estimate. Predict is one past estimation man. Test of hypothesis, for example, testing a p-value for BMI. You have to test, it's a wall type test for those two coefficients simultaneously equal to 0, and a p-value is derived with reference to a chi-square distribution with 2 degrees of freedom. So test parm, predict, all is available right after estimating a regression model. And so this is pretty much this is pretty much everything about this paper. And I hope this 45 minutes was kind of helpful to give you an idea of what you can do with Stata. And I hope this, if you want, I personally like also to add a histogram, in the spirit of overlaying data and predictions. I also like to overlay like a histogram of the distribution of body mass index. So you can see the position of the cases at the top, the position of the known cases at the bottom, adjusted odds ratio as a function of BMI, and then the underlying histogram, confidence interval, and a p-value. Okay, so of course, publication quality graphs are kind of time-consuming, but basically the most important command in Stata is two-way, and then you can overlay in the same plot region a histogram, a scatter plot for the position of the cases, and some line plot for the estimated odds ratios, and some common option like the legend, forget about it, of usually the odds ratios on the log scale, some Y label, X labels, the size of the figure, some titles, some text that you can add in the plot region, and then you give it a name. So this is Stata is very easy in terms of syntax. Of course, visualizations are never a free lunch. Okay, I think I'm done with this quick presentation and analysis of this paper, and we have a few minutes left, and if you have any questions, I'm happy to take them.
Yeah, thank you, Nicola, for the great presentation. Whoa, that was a lot of information in short time. Please note, everyone, that we have been recording this webinar, so we will be sending a link to the recording afterwards, so you can watch it in your own tempo as you like. There's a lot of information here, a lot of useful information. Yeah, and I think also, Nicola, you mentioned that you will include the do file.
Yes.
So
yes, I will share this do file. I'm going to add a couple of notes here, for example, test part, and then I'm going to share to you this do file. The data set, all the data are online. Everyone can access that, and the paper. I can also send you this PDF, so they go together. So you can so a PDF and a do file.
Yeah, great, thank you. That's very helpful. So then you can play around with this do file as you like afterwards. Yeah, we have some questions, and please, the attendees, just write your questions if you have any questions in the chat panel on your right, and we can try to answer them now. One of the questions here is what are the main advantages of Stata compared to free software like R and Python?
Yes. So the main advantage of Stata is documentation. Stata is 30 years old, and so they develop a lot of great documentation over the years. So it means that you can work with Stata offline. You don't have to spend an incredible amount of time over internet searches. Of course, like any documentation, it can be painful in the beginning, but as soon as you have all the worker examples, so Stata is the documentation is impressive. It's unbeatable. All open software there, you have to go over the internet, spend a lot of time for the methods and examples. Another advantage of Stata is that, of course, it's easy to use, user-friendly, and so you can pick up the language even for writing a paper for New England Journal of Medicine very quickly. So, and also it's very consistent. So once you learn, for example, I use some post-estimation command, test of hypothesis, or getting some predictions out of the model. This is extremely consistent, no matter what is the regression model, linear, logistic, longitudinal, survival, they all work in the same way. So that is an advantage. So it's a consistent, user-friendly, expandable. If you want, you can write your own command, you can write procedures that are not available and share it. There is a large archive of commands written by researchers willing to share what they need. So you have all the benefits of a commercial package, and also everything is certified, which it's a good thing. If you do research, you want things to be reproducible in many years to come. And so, I mean, accuracy, reproducibility, it matters a lot, and up to a certain decimal values. So I think it's nice to have a company dedicated to certifying and the scripts available. And and also if you're more serious in terms of programming, you also have that. We have matrix programming languages, object-oriented programming languages like C++, and which is available in Stata, within the Stata environment. If you want, it's not necessary, but for more advanced use, it can be useful.
Yeah, thank you. Good to know. You work with one data set for this demonstration. Can you work with multiple data sets?
Yes. So by default, when you open a Stata session, you can only have one data set at a time. And we saw this in the beginning when I was trying to import a data set from different formats. Stata complained us saying, well, are you sure you want to bring in a new data set? So in Stata, you can also work with data frames. So we have frames. So you have the default frame, but you can work with multiple data frames. So you can run different analysis of multiple studies simultaneously. You just need to say what kind of frame you are working with. So that is a new thing from Stata 17. And in terms of limits, the limits, how big are the data set? Well, it depends on your license. If you have multiprocessor license, you can work up to 1 billion observations. So it's quite, the limits are related to the memory, but nowadays it's not a big deal to work with. Even with a small laptop, you can work with very huge data sets. Okay.
Yeah, great, thank you. Yes, I think we will end the presentation there. It was really good to have Stata presented on our online demo days again. I think it's a few years since last time. So it was really nice to see Stata demonstrated again.
Okay. Thank you very much for having me.
Thank you for demonstrating, and have a nice day, Nicola.
Thank you. Have a nice day.